Once the protocol has completed, we navigate to the Data Analysis window and select the data folder that you want to analyze. Open the settings and browse for the appropriate preset file. Hit Close and Save, and then Analyze. This is the window you will see when the analysis is complete. There are 9 tabs along the top that are automatically generated, and we will be going through them one at a time. The first window is the raw data, also known as the differential absorbance spectra. This will show up even before the analysis is complete. Below the spectra is the table where the samples are listed along with their nominal concentrations. In the next window, the raw differential absorbance spectra are converted into the absolute absorbance spectra by normalizing for concentration and interpolating at 1 wave number resolution. You can also see in the table that since the system is quantitative, we now have a fit concentration that the computer calculates based on the reference protein designated in the settings. From the absolute absorbance spectra, the software automatically calculates the second derivative plot. This allows you to see the individual features that make up the protein spectrum more sensitively. This is particularly useful at observing small or subtle changes due to the increase in resolution and the extreme repeatability among replicates. The second derivative plot is then inversed and baselined to get a similarity plot. This is called the similarity plot because we calculate the percent of area overlap compared to a control sample that you designate by checking the AO compare checkboxes, and this quantitates the percent similarity. We usually observe a similarity of above 98% and higher among replicates, which gives us a high degree of confidence in the data quality and repeatability. Going back for a second to the second derivative plot, the software also provides a comparison by subtracting the second derivative plots of the samples compared to the control sample that you specify in the delta compare checkbox. This shows where the change is occurring in your samples compared to your control sample. Here you can see the most significant change is occurring at about 1656 wave numbers. Our stability plot tracks specific wave numbers from each sample to monitor trends in the data. In this example, we are tracking the wave numbers 1642, 1656, and 1680, which represents beta sheet, alpha helix, and beta turn, respectively. In order to calculate the secondary structure distribution, we use Gaussian curve fitting of the similarity plot. Here, you can see the curves that were fit to the spectrum. Since each curve corresponds to a secondary structure feature, such as alpha helix or beta sheet, we can then calculate the percent higher order structure and show it in this bar graph. Here, you can see as lysozyme is incubated at 60 degrees Celsius, it loses alpha helical content and it gains beta turn and beta sheet structure. This graph also demonstrates the high sensitivity of the AQS3pro. Overall, the key benefits of the AQS3pro are that it can accelerate development by catching instability earlier in the drug development process, and the fully automated workflow saves time and money because we can load and run samples in a 24 or 96 well plate. The improvements in data quality with the AQS3pro allow for analysis of proteins over the widest concentration range. This allows for analysis without buffer interference and yields repeatability around 98%, giving confidence in the data quality and ability to observe small changes. Finally, the AQS3pro de-risks drug development due to the increases in data quality, allowing confident, accurate, and timely decision-making. To learn more about what the AQS3pro can do for your research, visit us at RedShiftBio.com and request a custom demo. See change with the AQS3pro.